So, in general we may have functions of this kind and we want to find out whether they are exact or inexact. So, one of the conditions for a function to be exact is that we should be able to write it in the form in which we just wrote earlier. So, if we have a z which is a function of x and y, we should be able to write it in the form of dou z by dou x dx plus dou z by dou y dy. The first term y is constant and the second term x is constant. But for these kind of functions, the question is how do we find out whether it can be written in that fashion or not. So, one way of doing this again would be that we write what we had earlier. So, we have a general function z which is a function of say two variables x and y. Then we should be able to write this of course represents that y is constant when we are finding out this. This represents that x is constant when we are finding out this term. So, what we can do is take this term and differentiate it with this other variable with respect to this other variable. So, we have this term which is often called as some m or something like that, and this term which is also called usually as some n. So, what we have here is usually written as some m into dx plus some n into dy, where this n represents this and this n represents this. So, this is dou z by dou x. We can differentiate this with respect to y and find out the value. So, what we are essentially doing is take this m which is this term here and then differentiate with respect to y, and take this term here which is totally represented as n and differentiate it with respect to x, and compare these two values and see. So, this term essentially is, since m is dou z by dou x, this is essentially dou y of dou z by dou x. So, it is this. This term n is dou z by dou y, and what we are finding out essentially is dou by dou x of n. So, it is this. So, if these two turn out to be equal, then we call them as exact differentials. We call dz as an exact differential if these two turn out to be equal, and if these two terms turn out to be unequal, then we call dz as an inexact differential. So, mathematically that is how we can find out whether it is exact or inexact. Physically what it represents is, it represents either points on a graph or it depends something which depends on how you go from one point to the other, as we saw in the case of the map. So, here for example, we have we are moving from some point 1 to some point 3 and we have this value p dv. We want to find out whether it is exact or inexact. So, what we can do is we call this as some dz, and we can see that this is a function of two variables p and v. So, what we can say is over here z is a function of p and v, which means we expect dz to be something of the form of dou z with respect to the first variable. So, it is dou p at constant v into dp plus differential of z with respect to the second variable which is v. This has to be taken when the other variable is constant into dv. Now, we can compare what we have here with what we had from dz over here. So, we see that there is some term in front of dv. So, this term, comparing this and this term must be p and this term is 0. So, we have 0 times dp plus p times dv. Okay. So, this 0 represents dou z by dou p. What we are going to do is, so this is like the term m, this is like the term n. We are going to find out the differential of this with respect to the other term and the differential of this with respect to the other variable. So, we have over here after differentiating we still have 0, and here we have dou square z by dou v. We are going to find dou by dou p of dou z by dou v. Okay. So, we had dou z by dou v is p. So, dou by dou p of this is essentially dou p by dou p, which is equal to 1, and on the other side we had 0. So, we have 0 over here and we have 1 over here, and so this was essentially dou by dou v of dou z by dou p, okay, which is equal to 0. So, we see that we have 0 on one side and we have 1 on the other side, and clearly they are not equal. So, this function is not exact. So, this dz is an inexact differential, which means that this would represent a path function, something which depends on how we reach from point 1 to point 3. We could do a similar exercise with this, and I would encourage you to pause here and do it, and what we will find out is that this also is an inexact differential and it represents a path function. What we will do now is try the same exercise for this differential. Okay. So, we will once again write this as some dz is equal to p dv plus v dp. So, in general, so this means that z is a function of p and v as before. So, we expect dz to again be of this form on top. So, we expect dz to be dou z by dou p in at constant v into dp plus dou z by dou v at constant p into dv. What we are going to do is we are going to compare what we have here with what we have here. So, in front of dv we have p. So, this term is p. In front of dp we have v. So, this term is v. What we need to find out is differentiate this with respect to v, differentiate this with respect to p, and compare. So, we want to find out with respect to this variable v, which what was here, and we are going to differentiate with respect to this whatever is here, which in this case is p. So, we have dou v by dou v, which is 1, and on this side also we have 1, which are equal. So, what we see is that this differential is exact, which means if I find out the value of p dv plus p dp at any given location, it does not, if I find out the difference between point 1 and 3, it only depends on the value of this at point 1 and the value of this at point 3. It does not depend on how I got from point 1 to point 3. So, for example, if we were to look at the map again, if I found out something else, let us say p and v represent, they could still represent pressure and volume. If I wanted to find, I have some pressure and some volume at this location, specific volume I can think of, say density of air at this location. I have some pressure and some density of the air at this location. Okay. So, if I was to combine these in the way in which that function gave it to me, if I took the value, the difference in the value between point 1 and say this is point 3, if I took the difference in the value, it does not depend on how I got to point 3. As long as I am at point 1 initially and at point 3 finally, the difference in the values is the same. Whereas that is not the case with respect to, for example, other things like this. This would depend on how I got there. This does not depend on how I got there. Similarly, you should try out, for example, this differential and see whether you get the same thing. What I know is that you would get a different, you would get the RHS and LHS not being the same for this, which would tell you that this is inexact. So, we saw that this one was inexact we saw that this one is inexact, this was an exact differential, and you will see that this is also inexact. So, as I said earlier, the exact differentials represent properties or state functions, and the inexact ones represent path functions. We can do the same with, say, other functions of this kind. So, in this case we have a function here, it says del phi is some function of t into dt plus RT by V into dV. Let us say this is for an ideal gas, and what we want to find out is to find out whether this is a property or not. If it is a property, things are fine. If it is not a property, the idea is to find out what changes we can make such that this becomes a property. So, if it is not a property, the changes you need to make are such that dou square phi by dou t and dou v is equal to dou square phi by dou v dou t, right. That is what we want to find out. Over here R is a constant, what is called as the gas constant, which we will define a little later on, but for the time being you can just assume it to be a constant. So, we see that phi is a function of two variables, temperature and volume, and you can go through the same exercise as we did earlier and find out whether it is a property or not. And if it is not a property, you can change this original function such that it becomes a property, and the change can be in many ways. You can find out one or more ways in which you can change it such that this becomes a property. So, what I am going to do now is shift slightly. So, we have looked at inexact and exact differentials. So, we know what is a property and what is a path function now. I will not show you the proof of this, which I have on the next slide, because maybe I will leave it for you to try it out and ask questions if you are not able to find out how to do it.